Okay, hello everyone. Mr. Lau here. So what I'm going to do today is I'm going to go through lecture 4. All right. So what lecture 4 is about is actually, as the title imply, is actually the energy of liquid in motion. All right. So what we are going to study here today is more on the aspect of fluid mechanics. Okay, we want to really study how the fluid move and what kind of energy that is associated with the fluid itself. All right. So what are objectives of this module? Okay, or this chapter? Okay, first is to state the continuity of flow. All right. Second, to define the potential head, pressure head, velocity head, total head. Okay, and then to understand the concept of Bernoulli's theorem, and finally to apply the continuity and Bernoulli's equation. Okay, so what is the continuity flow? Okay, basically this is something that we already know. Okay, but just phrased in a different way. All right, this works based on something called the conservation of mass. All right, okay, because mass itself, okay, under the standard Newtonian physics, okay, cannot be destroyed or created. Okay, mass must always be conserved. Okay, so if we consider this pipe over here, all right, so we can say that whatever that goes in to the pipe, all right, must come out from the pipe itself. All right, so therefore, to derive this continuity flow equation, we will start off with this simple concept. M dot in is equals to M dot out. Okay, M dot over here, the dot here represents the rate. Okay, the units is given in kg per second. All right, so the mass flow rate, okay, is given by density multiplied by cross-sectional area multiplied by the fluid velocity. Okay, density meaning the density of the inlet fluid. All right, the cross-sectional area, okay, typically is usually considered as a rounded area, all right, which can be calculated by pi over 4 d1 square, all right, and of course your C1, which is the velocity of the fluid going in, which is equals to whatever that is coming out. So coming out, same thing, we have fluid rho 2, all right, fluid velocity C2, and of course your A2. So A2 can be calculated by pi over 4 d2 square. Okay, that is the cross-sectional area of a circle. Okay, for those who are not very sure how do I get this pi over 4 d2 square, all right, the area that we are familiar with is actually pi r square. Okay, but r is diameter over 2. All right, so from here we can get pi over 4 d square. So typically in the industry, we calculate area based on the diameter. Nobody will go and measure half the diameter because it just doesn't make sense. Or for the pipe, okay, the diameter can be easily obtained by measuring from one side to the other. Okay, can. So therefore, we start off with m dot 1 equals to m dot 2. All right. So we assume that the density of the water coming in is equal to the density of coming out. Okay, this is what we call the incompressible flow. All right. So if that's the case, we can cancel away the rho 1 and rho 2. Okay, and we are left with A1C1 and A2C2. Okay, can. And A1C1 itself, okay, is actually the volumetric flow rate. Okay, so it can be written as V1 dot. So this is the volumetric flow rate. Okay, can. So this will be the final form. In fact, we seldom use V dot 1 equals to V dot 2. We usually start off straight away with A1C1 is equals to A2C2. All right, so all of this, okay, is under the assumption that it is incompressible flow. All right, which means that mainly we are dealing with liquid over here. All right, because usually for gas is compressible. Okay, for gas, the density can change because we can change the volume. Okay, because we can compress it. All right, so this formula might not apply entirely under certain condition. But if you're talking about just liquid alone, then density should usually be the same and it can be cancelled off. Therefore, A1C1 must be equal to A2C2. Okay, so actually that's all. That's all for the theory part of the continuity equation. Okay, we can go through this example here, 3.1. So oil flows through a pipeline which contracts from 450 mm to 300 mm diameter at B, and then forks out, one branch being 150 mm at C, and the other branch being 2 to 5 mm at D. If the velocity at A is 1.8 meter per second, okay, so if the velocity here, CA, is 1.8 meter per second, and the velocity at D, CD, so remember the velocity, we'll write it in terms of C, all right, okay, because V is reserved for volume. Okay, so what they are asking for is the discharge at C and D. Okay, so I want you to bring your attention to this word called the discharge. So discharge in our context is actually the volumetric flow rate. So what they want is actually V dot C and V dot D. So this is what the question wants, the discharge at C and D. Okay, of course, they also want the velocity at B and C. So we need to find out what is your CB and CC. All right, Ken. So how do we start off the question? So we can actually find out V dot A easily. Okay, the discharge at A will simply be given by cross-section at A multiplied by velocity at A. Okay, so remember the formula I mentioned just now, pi over 4 d squared. Okay, take note, the d given to you from the previous part is in terms of mm. So you must divide it by 1000. Okay, velocity at A, 1.8, and you can get this answer. Similarly, for VD, okay, ADCD, all right, pi over 4d squared, okay, same thing divided by 1000 times 3.6, and you can get VD. All right, so we are done with calculating the discharge at A and D. Next, all right, we need to find out the velocity at C. So how do we get CC? So to get CC, we must first obtain VC. So to get VC, we need to apply the continuity between AC and D. All right, so if I draw back the diagram here, okay, the diagram was supposed to be something like this. Okay, just a rough sketch. So A, C, and D. So continuity basically means that everything must be conserved, meaning to say that whatever that enters through A must be equals to whatever that leaves from C and D. So therefore, logically speaking, we will write VA is equals to V dot C plus V dot D. It's just a common sense equation. All right. So if we rearrange them, we can find out VC. So VC is basically VA minus VD. Therefore, this will be our VC. Okay. So nothing too difficult. Basically, it's just asking you to apply the concept of conservation. All right. So same thing. Okay. To get our CB, which is the velocity at B, we need to find V dot B. All right. So to get V dot B, okay, we will simply apply the continuity between A and B. So this was the fork again. So A was this point, B was this point. So if we apply the continuity, okay, let me get the color. Okay, between A and B. All right, that means to say that whatever goes in through A must come out from B. Okay, because there's no other network. So whatever comes in from here must go out from here. So V dot A is equal to V dot B, therefore V dot B is also 0.286. Okay, having said that, it's important to take note that you can apply continuity, all right, in the network, okay, in whichever location. All right, can. But most importantly, the concept is it must be logical, the fluid must be conserved. All right, So for this question, we saw ourselves applying in two different locations. One is A and B, and the other one was between A, C, and D. Okay, so once we have our VC and our VB, okay, simply we apply our AC, okay, and we can get our velocity at C and velocity at B. Okay, so that's it. Okay, so for this chapter, we are only going to deal with two main equations. Continuity was the first one. The second one will be your Bernoulli theorem. Okay, can. So the Bernoulli theorem will be the core, okay, of pre-university fluid mechanics study. Okay, in university or in tertiary level, okay, we are going to learn something more sophisticated, something more universal, which is called the Navier-Stokes. So for those who are interested, you can actually go and take a look at something called the Navier-Stokes. So the Navier-Stokes equation is actually the main equation used in the world of fluid mechanics. Okay, the rest is just a simplification. So Bernoulli theorem, okay, is just a simplified version of the Navier-Stokes. How do we simplify it? We simplify it by using certain forms of assumptions. Okay, but that is not in our scope of discussion today. All right, so we are not going to go venture further into that. For those who are interested, you can go and take a look. All right. Okay, can. So the simplification will let us arrive at Bernoulli theorem. So what is Bernoulli theorem? Let us derive it. Okay, so again, we will consider this same slanted tapered pipe. Okay, fluid entering through one, all right, and fluid and leaving through two. Okay, can. So for one, all right, there's a few parameters we need to take note. There's your pressure at one, P1, C1, and Z1. Okay, P1 is pressure at 1, C1 is velocity at 1, Z1 is the height at 1 with respect to something we call the reference line, or we call it professionally datum. Okay, same thing at the outlet, alright, we also have these three terms. One is your P2, C2, and Z2. Okay, and so we are going to assume this generic example. Okay, so a few assumptions over here for this Bernoulli equation to be valid. Okay, the first thing is all corresponding points on 1 and 2 must be on the same streamline. Alright, so basically what this is trying to say, okay, just let me give you a quick understanding on this, is that, alright, because each of the particles, the water particle, will actually flow. Okay, they'll flow along this thing, a path, and end up here. Okay, these paths are called streamlines. So for this Bernoulli theorem to be valid, each particle must have its own path. The paths cannot cross one another. All right, so this is what it is trying to say. Okay, whatever that is flowing must remain in its own path. Okay, can. Second, okay, of course the fluid is incompressible, meaning to say that the density must be the same. Rho 1 must be equal to rho 2. Okay, the flow is steady. Okay, so steady meaning to say that whatever goes in is coming out. Okay, at steady state, which means to say that m dot 1 must be equal to m dot 2, or v dot 1 is equal to v dot 2, which is the continuity that we studied previously. Okay, and lastly, okay, for the perfect equation, okay, we assume that there's no frictional loss throughout the flow. All right, so we apply the conservation of energy. Okay, so the next step is to apply the conservation of energy. So conservation of energy will tell us that rate of energy in must be equal to rate of energy out. So the question is, what is the energy going in? Okay, so when the fluid actually goes in, all right, it will bring it along three different types of energy. Okay, we have the potential, the kinetic, and the pressure energy. Okay, so the potential energy can be written as m dot gz, whereby z is the height, okay, from the datum. kinetic m dot c square over 2. Okay, all these two formulas must be very familiar for you guys because it's just mgh and half mc square. The last time that we learned it in secondary school. Okay, the last one is actually the pressure energy. Okay, this pressure energy is actually something that we have also learned before. Okay, if you recall from chapter 2, okay, we discussed about something called the energy required to push the fluid into the system. So it's just like you when you want to go into the room, you need to use energy to open the door. So for the fluid to go in, okay, you must apply pressure and push yourself in. Okay, so for the fluid coming in, you carry with it 3 different types of energy. All right, so we are going to do some simplification. All right, so from the total energy, we are going to divide throughout by m dot g. M dot meaning the mass flow rate and g being 9.81. Okay, so once we divide, the m dot g can cancel off for the first term, m dot can cancel for the second term, and the n dot can cancel for the last term. So we leave ourselves with z plus c square over 2g plus p over rho g. Okay, so the consequence on the left hand side is when you use the total energy divided by m dot g, it gives us something called the head. Again, this head concept has been discussed before in the previous chapter, chapter 3. Okay, whereby we talk about the pressure head. Okay, so for the pressure head that we studied in chapter 3, is actually part of this equation. If you can see, let me just change to my marker ink. The pressure head that we studied in chapter 3 appeared here. P over rho g. Remember, P was rho g h. So H was P over rho g. So in chapter 3, what we actually studied is something called a static pressure head. Because if you recall in chapter 3, nothing was moving. Everything was contained in a manometer, in a barometer. Nothing was moving. So the pressure that we measure over there is considered static pressure head. But over here in chapter 4, the main difference is the fluid is moving from the inlet to the outlet. Since the fluid is moving, so there should be other forms of associated energy. Okay, of course, the most obvious one is your velocity head, c squared over 2g. And of course, your potential head. So the potential head is due to the height, okay, of that cross-sectional area itself with respect to the datum. So how high is it depends on how high is it will determine how much potential it has. Velocity head depends on the fluid velocity, and the static pressure head, all right, is the static pressure. All right, and this will give us something called the total head. So again, we don't want to talk about this energy in terms of joules. Instead, we try to associate this energy in terms of heat for easy comparison. All right, so typically if we talk about heat, meaning to say if let's say we have a pump A and pump B. So if pump A provides 10 meters of heat and pump B provides 1 meters of heat, of course pump A is more powerful than pump B because it can pump up to 10 meters of heat, 10 meters worth of energy. That's what we are trying to say here. All right, so we'll discuss that further a bit later. All right, so with that, since the total head is given by this, so the total head in must be equal to the total head out. So Z1 plus C1 square over 2G plus P1 over rho G must be equal to Z2 plus C2 square over 2G plus P2 over rho G. Or we can simply write Z plus C2 square, C square over 2G plus P over rho G must be constant. So this, ladies and gentlemen, is our Bernoulli's theorem. Okay, so with that, we can quickly go into an example. Okay, we just want to apply the equation. So we have beer with specific gravity of 1.06. All right, so take note, remember the concept of specific gravity. So if the specific gravity is 1.06, meaning to say that the density of the beer is 1.06 times 1000, which is 1060. It flows at a rate of 30 meter cube per minute through the taper pipe as shown below. The cross-sectional area of the inlet is 0.25 and the pressure drop of 2 bar is recorded between the inlet and outlet. Neglecting all losses, determine number 1, the decrease in pressure head. Number 2, the velocity at inlet and outlet. Number 3, okay, what effects will it have if the pressure head and the velocity head at the outlet of the specific gravity 1.10 flows through the pipe. Okay, let's talk about the number 1 first, the decrease in the pressure head. Okay, so at this point, I need to point out to you that even though we have mentioned something called the total head, all right, but we are not going to confuse things. Whatever that we measure at 1 and measure at 2 is simply just the pressure. Usually, whatever we measure is only the pressure, the static pressure. Okay, the total head will not come out at all. Total head is only in the equation itself. We can still measure total head, but with a special device. But whatever that we're going to measure here, that means if I put a open manometer here at this point and open manometer at this point, it's going to give me just the static head, P1 or H1 or H2. This is the static head. Okay, so don't be too afraid of the term total head. Total head cannot be measured at this point yet. All right, can. So what is the decrease in the pressure head between the inlet and outlet? So the drop of pressure of 2 bar, okay, is recorded. So we're just going to use this 2 bar straight away. So to get the drop in pressure head, all right, we are going to use this formula, delta P over rho G. Okay, this is how we get the head from chapter 3. Okay, so drop in pressure is 2 bar, so change it to SI unit, 2 times 10 to the power of 5. Rho is the density of the beer, and 9.1, so it's equivalent to 19.2 meters of beer. That means the total drop in pressure from inlet to outlet is associated with 19.2 meters of beer. It's equivalent to 19.2 meters of beer. Alright, again, we are not going to talk about energy, we're not going to talk about pressure directly, but instead, we are going to associate with something called the head with the units as meters. Alright, next for part B. So for part B, we want to get the velocity at the outlet. So how can we get the velocity at the outlet? Okay, so we have to apply our Bernoulli equation. But before that, first, we can apply the discharge equation. So V dot 1 is equals to A1C1. Okay, so V dot 1 we have is given to be 30 meter cube per minute. So we got to divide by 60, alright, to change it to per second. Okay, pardon for the aeroplane. I have no way to control it. Okay, so A1 is given to be 0.25 times C1. So therefore, C1 is simply 2 meter per second. So we apply Bernoulli between point 1 and 2. Alright, so for point 1, we have the left hand side. Point 2, we have the right hand side. Okay, our objective is to find out my C2. Okay, so we can actually calculate the values that we are given. Okay, so what we can do is we make C2 the subject and shift everything to the right hand side. Alright, so the first term over here, P1 over rho G minus P2 over rho G, that one is actually our pressure head drop. So this term here is our pressure head drop that we have calculated in part A. So this is simply 19.2. Z1 is 1 meters and Z2 is 15.34. That's given by the question. C1 we have already worked out, which is 2. Therefore, we can simply calculate C2, which is 9.97. Alright, can. Next, for part C. So what happens if we increase the specific gravity of the beer? That means we make everything denser. Okay, this is the under the assumption that the 2 bar pressure drop remains the same. Okay, the 2 bar pressure drop remains the same. So what will happen to the pressure head? So since the pressure head was given by delta P over rho G, if I increase my density, okay, the total pressure head will drop. So therefore the pressure head will decrease. Okay, can. So using back the same assumption, if my pressure head decrease, alright, since where is my pressure head? My pressure head was inserted here, 19.2 previously. So if this pressure head drops, meaning to say my C2 will also drop. Alright, so take note, this is under assumption that by the pressure head remains the same, 2 bar drop. So if my density increase, my pressure head drops, and my pressure head drops, the velocity will also drop. Alright, can. Okay, of course, we are not going to only stop at this Bernoulli equation. We need to do some certain modification. So this modification will include energy input, output, and any form of losses. So for fluid mechanics itself, a significant source of energy input, of course, will be a pump. All right, and of course, the significant energy output, all right, will be in the form of turbine. Okay, because turbine extracts energy from the fluid flow, pump inputs energy from the fluid flow, and the losses will mainly occur due to friction. When the water flow within the pipe or through your uh, valves and stuff, okay, it will lose energy due to friction. All right. So what we are going to do here is we are still going to apply the Bernoulli equation. So let's see if we apply it between 1 and 2. Okay, remember when we apply the energy in Bernoulli equation, it was based on the fact that its energy in is equals to energy out. So whatever is on the left hand side must be the input. So from 1 to 2. So going in from 1, okay, of course will be the fluid energy. Let me change the ink. Okay, so whatever that goes in at 1 is the energy that brought in by the fluid. So the energy that brought in by the fluid, there's 3: potential head, kinetic head, and pressure head. Alright, and of course, since I need to put all the inputs on the left, from 1 to 2, between 1 and 2, okay, when the water flows from 1 to 2, the one significant source of input will be H pump. So H pump will be on the left. Right hand side, output. So output at 2, okay, fluid flows out. So it brings along with itself 3 different types of energy: potential, kinetic, and pressure. Okay, and since output must all be on the right, okay, when the water flows through the whole pipe, significant source of output is H turbine. Alright, the turbine will extract energy from the flow. And the last one will be your H losses. The H losses is due to the friction. Alright, so this will be the modified Bernoulli equation with complete energy input, output, and losses. Okay, but just like the continuity equation, we can choose the position where we apply the Bernoulli equation. It doesn't have to be for the entire system because certain parameters of the system might be unknown. So let's say if I only apply between 1 and 3, okay, so between 1 and 3 will be the fluid energy at 1, input there's only a pump, okay, but between 1 and 3, the fluid flows out from 3, so we have the parameters at 3, and the only output we have is the H losses. There's no turbine between 1 and 3. Right? So if you can see, if you can trace out the fluid path between 1 and 3, you realize that there is no turbine from 1 to 3, there's no turbine, so we won't include turbine. Same thing if we do 3 and 2. So 3 and 2 will be fluid flowing through 3, okay, and fluid exiting from 2. All right, and then of course from 3 to 2, let me trace out the path again. From 3 to 2, uh, from 3 to 2, which is from here to here, you will bypass one turbine, which extracts energy, and of course there will be frictional loss. Okay, so but I need to bring your attention to this is that the H losses for the first equation and the second equation and the third equation is all different. Because for the first equation, the H loss is dependent on the fluid path. So from 1 to 2, the fluid path is the complete path. From 1 to 3, the fluid path is shorter, and 3 to 2, the fluid path is also shorter. Okay, so the losses itself actually is summative. So we can actually say that if we compare the losses here, the losses at 1 must be equals to that of 2 plus 3. But individually, they are different because the losses is due to friction. The friction depends on how much the fluid actually travels. Okay, that's why it's important to trace out the path. All right. Okay, so very good. We'll come to this example, okay, to discuss the use of this modified Bernoulli equation. All right, so we have an AB section. There is an inclined pipe. All right, and let me just change the color of my pen. Okay, diameter 50 mm and 10 meters long. A is 7 meters below B. Okay, and assuming that the head loss is given by this. So usually for our case, at this point in time, the head loss will be given by a fixed equation. Okay, but the head loss is dependent on C, the velocity. Okay, take note the head loss is given as 0.5 c squared over 2g per meter length of pipe. So it depends on how long your water travel. It travels 1 meter, you times 1, 2 meter times 2, 7 meters times 7. Okay, whereby c is the velocity of the water in the pipe. Calculate the pressure difference between A and B if the water flows at 0.01 meter cube per second, and 2, the water flow rate if the pressure at A is greater than B by 200 kilonewton per meter square. Okay, so first of all, we look at the schematic. Remember, in the exam, if the schematic is not given, try to draw it out yourself. Whatever that we give you, it's not going to be complicated. You can definitely hand sketch it yourself. All right. So over here, before we start, I will set A as the datum. Okay, or the reference line. Okay. So we already know that A is 7 meters below B. So this is 7 meters. All right. Okay. The length of the pipe is 10 meters long. Okay, the cross section of the pipe is 50 mm. That means it doesn't change. The cross sectional area here and the cross sectional area here is the same. All right, so let's move on. So how do we get the pressure difference? Okay, so first of all, we need to get the velocity. So same as previous question, we need to apply the discharge equation. So V dot is equals to AC. A can be calculated by pi over 4d square, standard. Okay, d is given in mm, so divide by 1000. So we can get our C, 5.1 meter per second. So today, so long as the cross-sectional area of the pipe doesn't change, the velocity should remain the same throughout the whole pipe. Okay, so that is something for you to remember. You can memorize it. If the cross-sectional area doesn't change, and there's only one way in and one way out, the velocity will never change. So next, okay, we'll take A as the datum, as I mentioned just now. Okay, it's important to define your reference. Okay, so we apply Bernoulli between A and B. So again, all right, where is the inlet? The inlet only has a fluid coming in from A. All right, is there a pump? There's no pump. Outlet will be the fluid going out from B. Is there a turbine? No turbine. So there's only head losses. All right. Okay, so we are asked to find the pressure drop, the pressure head drop. Okay, or pressure drop. So we are going to rearrange the equation. Okay, we are going to put PA over rho G minus PB over rho G on the left hand side. Group the rest of the terms together. ZB minus ZA, CB minus CA square, and of course your H losses. Take note of your H losses equation is given by the formula given to you times your length of pipe. Okay, so first we'll put in the values. ZB is 7 and ZA is 0. Why? Because we have already determined A as the reference. So if A is the reference, ZA will be 0, ZB will be 7. If it is the other way around, if I set B as a reference, then things will be different. If B as the reference, B will be 0 and A will be negative 7. Alright, so it depends whether is it higher or lower. So if A is the reference, B is higher, so it's positive 7. There's no change in velocity, so it's 0. And for the losses, okay, apply the equation, and since it goes through a 10 meters length, so this will be times 10. And this will give me 13.63. At this point, the units is actually in meters. This value here is actually your pressure head drop. Alright, but what the question wants is the actual pressure drop. So we got to shift the rho G to the right hand side, times rho times G. Sorry, times rho times G. And this will give you the actual pressure drop. Alright. Okay, let's move on. Okay, the part B. Alright, so now for part B is given the other way around. We are given the pressure drop instead. And we are asked to calculate the discharge. Okay, so it's the same question but asked the other way around. So since asked the other way around, we've got to reverse the whole process. So first we'll apply the Bernoulli equation. So it's the same equation. Alright, we're going to plug in the values. Okay, we're not going to do anything with it. Just going to plug in the values. So today H losses will be given by 0.5 c squared over 2g times 10. There will be no change in your velocity. Alright, same thing, ZA is 0, ZB is 7. Okay, and your PA minus PB is given to be 200. Okay, so today if you calculate the right hand side here, okay, you press the calculator, it will give me 13.39. Okay, so maybe I just rewrite it here. So it's 0.5 times c squared over 2g is equals to 13.39 times 10 also. Okay, so to get my c square, so this will be c square is equals to 13.39 times 2g divided by 10 times 0.5. Alright, so if you bring the square over, you'll give us square root. So this will give me my c value. So today the unknown is actually in c. And this c happens to be in the H loss. Okay, so once we have the c value, we can apply the discharge to find out my v dot. So AC, and this gives me my v dot. Right? Okay, the next example. Okay, the next example we are going to look at a siphon. A siphon is discharging water as shown in the figure. The frictional loss in the pipe is again per meters of the pipe. Oops. It's again per meters of the pipe. Okay, where c is the velocity. So we are asked to calculate the length of the pipe under the water level when the velocity of the water in the pipe is 0.8 meter per second. Okay, so what this question is trying to ask is, what is this length? Here. Okay, so what we are going to do here to solve for part A is actually to apply the Bernoulli equation. But as I say, when you apply the Bernoulli equation for this system, which is slightly more complicated, we need to choose the 2 points. Okay, so here, before I go into the solution, I'm going to tell you that I'll give you some advice on choosing the points to apply the Bernoulli equation. So today, typically, I will choose, for this question, all right, I will choose point A and D. So for part A, I will most likely be applying Bernoulli between A and D. Why? Okay, because there's a very important thing about A and D is that A and D is exposed to the atmosphere. All right, so if it is exposed to the atmosphere, it means to say that PA will be equals to PD will be equals to 0. The gauge pressure is considered 0. Okay, bear in mind when we apply all this equation, what we are using, okay, is actually the gauge pressure. All right, so PA must be equals to PD must be equals to 0. All right, so that's why we will choose between A and D. Okay, and more importantly, the length of the pipe that's under the water must be enclosed by the 2 points that we select. So between A and D, if we trace the path, it will bypass the unknown that we need. All right, so we'll choose A and D to apply, and of course please take A as your datum. Okay, so we apply the modified Bernoulli equation, inlet, outlet, and there's losses here. All right, so the length that we need is actually hidden in H loss, because when we look at the H loss formula, is 1.5 c squared over 2g times the length of pipe. So the unknown is hidden in this length of pipe. So we make H loss a subject, and rest I put it to the right hand side. So ZA minus ZD. So what is ZA? So if we take A as the datum, ZA is 0. How about D? D, all right, in this case is 0.5 meters below A. So as I mentioned just now, if it is below, it must be negative 0.5. Okay, can. Next, CA minus CD. So CA is 0. Okay, why is CA 0? CA, all right, A is on the water surface. Okay, usually we will consider the water on the water surface to be not moving. So CA is approximately 0. Okay, so that is another reason why I would want to choose A as one of my point. Because if I choose A as one of my point, straight away I can eliminate two values. PA is 0 and CA is 0. Okay, so relatively constant. So CA is 0. And CD is given to be 0.8. Okay, and again, PA minus PD itself is 0, as I mentioned. So if we let X be the length of the pipe under the water, so the total length of the pipe that the water went through was how much? Let's go back and calculate. All right, the total length of the water went through is, let me change the color. Okay, firstly is this part, the unknown X plus 2 meter plus 6 meter. So X plus 8 total. Okay, the right hand side will be 0.467 and we can get the X value. Okay, can. So remember, the selection of the Bernoulli application points is important. Okay, next, what the question wants here is, oops, sorry. Okay, we want to calculate the pressure at B. So if we want to calculate the pressure at B, we must take the Bernoulli between A and B. We cannot take A and D because we want B. All right, but we will still retain A because A gives us a convenient value of CA being 0 and PA being 0. All right, can. So we apply the equation. Okay, can. So same thing, A is the datum. So we shift B to the left hand side. So ZA is 0, ZB is 2 meters above A. If you look at the diagram, CA again is 0, CB, okay, is again still 0.8. Why? Because if you look at the siphon pipe, the diameter of the siphon pipe doesn't change. So if you recall just now I say, if the diameter doesn't change, the cross-sectional area doesn't change. If the cross-sectional area doesn't change, the velocity doesn't change. So CB will be the same as CD, 0.8. Alright. Next, for PA, okay, I've given two options here because two options are possible. Alright, you can either choose to use the absolute value, which is 10 to the power 5, because it's atmosphere. Or you can choose to what I say, use PA, which is gauge. So this is the better option because it's 0. Alright, so we'll see the consequence of that. So we'll just put in the values, everything. H losses. H losses today, be careful, because we are not going to go through the whole pipe. We are going to go through only from A to B, only until here, from here to here. So the distance that we travel within the pipe is only 3.54 if we add it up, which is 2 plus 1.54. 1.54 under the water, 2 from above the water to the point B. Okay, so we work out the right hand side. It will be negative 2.206 plus either you choose the absolute value or the gauge value. But again, gauge value is convenient. So we work out the PB. So again, I give you a choice, either use absolute or gauge. If you use the absolute value, alright, you will get the absolute pressure. Alright, if you use the gauge, you'll get the gauge. But don't worry, both answers are acceptable. Alright, because to get the absolute from the gauge, you just need to add the atmosphere to it. Alright, so typically for fluid mechanics, usually we'll just use the gauge pressure. If we need the absolute at the end of the day, we'll just add back the atmosphere. Alright, in this case, take note this is vacuum pressure, negative. Why? Because it's below the atmosphere. Alright, can. Okay, the next example we have here is something that involves a pump. So the pump draws oil, okay, specific gravity is 0.82 from an open reservoir. So if the specific gravity is 0.82, the density of oil is 0.82 times 1000 from an open reservoir and delivers it to the base of the closed tank as shown in the figure. The air pressure above the oil is a closed tank with 55 kilopascal gauge. The total heat loss of the system is 25 c squared over 2g. So take note, this question is slightly different from the previous two because it's giving you the total heat loss. It's telling you that total, when the fluid moves through the full system, is 25 c squared over 2g. It's no longer in terms of per meters. So it can be presented to you in two ways. One is in terms of per meters, which then you have to multiply by the length traveled by the water within the pipe. Or in this case, you just need to consider it as a whole, which is 25 c squared over 2g. Alright, c is the flow velocity, and the diameter is 65 mm, and the discharge is 9.5 liter per second. Calculate the pump head developed. Alright, so we are interested in the head of the pump. Okay, so how are we going to do it? Okay, first step, same thing, we're going to use our discharge equation to find out my velocity first, because without velocity we cannot work the Bernoulli equation. Alright, so then we'll apply the Bernoulli equation between where and where, which is two good points to take that will enclose the pump, because we want to find the pump, so you must enclose the pump. So of course, the point that we'll take is between 1 and 2. Why? Firstly, for 1, we know that C1 will be 0. And P1 gauge will also be 0. Why we choose 2? Because C2 is 0. And P2 is given as 55. Alright, therefore we'll choose 1 and 2. Alright, and today we'll take 1 as the datum. Okay, so we apply the Bernoulli between 1 and 2. Inlet fluid coming through 1. Energy input H pump on the left hand side. Outlet and of course your losses. So what we want to find is H pump. So we'll put the H pump to the left and put the rest on the right and group them up. So first of all, Z2 minus Z1. So what is Z2 minus Z1? Z1 is clearly 0. What is Z2? Z2 is the height from 1. So what is Z2? Z2 is 2.2 plus 7.15. Okay. What about C2, C1? 0, 0. Because as I mentioned, because they are on the surface of a tank, so it's 0, 0. Okay. P2, all right, we'll use the gauge pressure of 52 kilopascal. So remember to multiply by 10 to the power 3. P1 is 0. Okay. The losses, okay, is the full losses. So it's 25 times C square over 2G. C square, we found it to be 2.86. So this will give me 26.61 meters of oil. So what we have here, ladies and gentlemen, is the pump head of the pump. So what does it mean? It means that this pump, okay, has the equivalent energy to pump oil to a height of 26.61. That means if I were to take the pump and work it alone, it will be able to pump the oil to a static height of 26.61 meters. That's how we associate the power of the pump. How powerful is it? So it's 26.61 means that if I were to on the pump and operate it alone, you can pump the head up to 26.61 meters of oil. Okay, but of course in this context, okay, we don't associate with that. We just say that the head of pump is 26.61. All right, I'm just giving an analogy. If I operate the pump in a standalone context. All right, so if not, that's it for this chapter. Thank you. All right, hopefully you understand and learn much from this chapter. Okay, it's not easy. Okay, but you need to try to understand it and try to do some of the tutorial to increase your understanding. All right, if not, thank you so much. See you again.